Hi, in this video, we are going to do a slightly different analysis of the Grover search algorithm. So recall that Grover search algorithm works in a two-dimensional space. So let me draw this space for you. This is psi s perp. Psi, this is a solution space. And the initial vector is this uniform superposition vector psi. And the angle is theta over 2. So psi, the initial input to the Grover search is square root of n summation over x uniform superposition vector. And the Grover iteration consists of two operators, this u of f and r psi. And u of f is the reflection about um, the vector psi s perp. So it takes, it takes the vector psi to this reflected vector um, right? So it reflects first about this vector psi as perp and then reflects about the vector r, r, r psi is a reflection about ket psi. So you get the final vector which is at an angle theta towards the solution. So this is the solution space. So the vector psi is driven towards the solution space by an angle. Right. So in fact, Grover operator G is a rotation operator. If you rotation operator in the two-dimensional space, which is the span of psi s and psi s perp. So you take the basis as the two-dimensional space, and the rotation matrix, as any other rotation matrix, is given by cos theta minus sine theta cos theta. Right. So this is, if we restrict ourselves to the two-dimensional subspace spanned by this, then the Grover operator is a rotation matrix which is given by this matrix over here. And recall that sine theta over 2 is square root of m over n. Right. So now we are going to analyze the Grover operator by looking at the eigenvectors and eigenvalues of this Grover operator. Okay, so well, we have to look at the rotation matrix. If I restrict myself to a two-dimensional space, as you know, don't have eigenvectors if I take them over the real field. But if we expand it to the complex field, then they do indeed have eigenvalues and eigenvectors. And so the eigenvectors and eigenvalues of the G, so eigenvectors and eigenvalues of the Grover operator G are the following. So let me say that suppose I take psi s perp, if I denote to be ket 0 and psi s to be ket 1, then the eigenvectors of this Grover operator are alpha 1, ket alpha 1, which is ket 0 minus I ket 1 over square root of 2. So this is an eigenvector with eigenvalue e to the I theta. And the second one is alpha 2, which is ket 0 plus I over square root of 2, and with eigenvalue e to the minus I theta, which means that G applied to alpha 1 is equal to e to the I theta alpha 1 and G applied to alpha 2 is equal to E up to the minus I theta. This is the eigenvector eigenvalue equation. And our initial state psi is equal to cos theta over 2 get 0 plus sine theta over 2 get 1. Right? In fact, we can write the state psi in terms of the eigenvectors. So eigenvectors alpha 1 and alpha 2, the span also form a basis of our two-dimensional vector space. And we can always write this vector psi in terms of the basis of eigenvectors. And it will be clear why we are doing that. So if we do that, then I can write this as e to the I theta over 2 alpha 1 plus e to the minus I theta over 2 alpha 2 get alpha 2 over square root of 2. And this can be done by just using these equations and this equation, right? Now, what's the use of that? So what happens when we apply G to psi? We get, if I apply one iteration, I'll get G to the I theta over 2. Due to linearity, we'll get G applied to alpha 1 plus e to the minus I theta over 2, G applied to alpha 2 over square root of 2. And therefore, this becomes G applied to ket psi is e to the I theta 2 plus theta alpha 1 plus e to the minus I theta over 2 plus theta alpha 2 over square root of 2. And then if I repeat this, let's say t times, then G applied to t will be e to the I theta t plus theta over 2 alpha 1 plus e to the minus I theta t plus theta over 2 alpha 2 over square root of 2. Right now, it will be clear why we are doing this, because now if I want to compute the probability of success, which means if I, after t iterations, probability of success will be G of t ket psi, and it will be inner product with 1 mod square. And this will be easy to compute from this equation, right? So I have, this is just, this equation is just writing my original vector in terms of the eigenvectors of G. And then that makes it easy to compute G to the power t. And then using these equations, this equation in particular, right, I can write that this will be P of t will be equal to get 1, then e to the I theta t plus theta over 2 alpha 1 plus e to the I theta get 1 e to the minus I theta t plus theta over 2 alpha 2 over square root of 2 and the whole mod square. Now, how do we compute? So we need ket 1 alpha 1 and ket 1 inner product alpha 2. That we can find from over here, these two equations, right? So ket1 alpha 1, for example, will be minus I over square root of 2, and ket1 alpha 2 will be I square root of 2, right? And we substitute them over here, and you will see that probability of success after t iterations will be exactly equal to sine square theta t plus. And the rest of the analysis from this point is exactly equal to the Grover search analysis that we did earlier. So if we iterate by t equal to pi over 4 square root of n over m iterations, then we'll be very close to the getting a high probability of success, and the success probability, as we had found out earlier, will be greater than 1 minus cos square theta over 2, which is equal to 1 minus m over n. Okay, so what we have done in this video is that we gave a slightly different analysis of the Grover search iteration. And the key idea is that we have to notice that within this two-dimensional space, the Grover iteration is a rotation operator. With parameter theta. So the matrix is given by this matrix, where theta, sine theta over 2 is square root of m over n. Now the key idea is to find the eigenvectors and eigenvalues of this equation, which are given by alpha 1 and ket alpha 2 with eigenvalues e to the I theta and e to the minus I theta. And then write our initial vector in terms of those eigenvectors and eigenvalues, which is right over here, right? And then when we iterate, we don't have to work a lot because of the eigenvector eigenvalue equation. G to the t theta, g to the t psi can be easily calculated. And then the success probability is just the inner product with the solution space mod square. And then we get this success probability is equal to that. And the remaining analysis is similar to the previous analysis, and we get the success probability to be greater than 1 minus cos square theta over 2. All right.